What I'm going to talk about here is I'm going to talk about rearrangements in addition reactions, specifically hydrohalogenation. In a previous video, I walked through why we saw hydrohalogenation, what happened, how we got to where we are. One thing that can happen, though, as we'll see, was referred to as rearrangement. Rearrangement, I'm moving things around. And I could describe it, but it's going to be easier to show you here. So I've got this chemical compound. It's an alkene. I'm reacting with hydrogen iodide. So this is going to be an addition reaction. This is going to be a hydrohalogenation reaction. Now, I'm going to draw what we would expect. We know that HI will give us a Markovnikov product. What's Markovnikov? Hydrogen adds to where there's already more hydrogens on the double bond. So this carbon has 2 hydrogens, this carbon has 1. My hydrogen's going to add to the more hydrogenated carbon, and the iodide's going to add to the other one. So I'm going to draw that first. So this is what I would expect. I added a hydrogen to this carbon, the iodine adds to the other one, and then I have this mess over here which is just alkyl stuff. I'm not worried about the alkyl stuff normally. So this is what I would expect. So I'm going to write expected. And don't get me wrong, we do see some of this. We see probably a decent amount of it. But it's not our major product. It's not what we get most of. What we get most of, well, let me draw it first. This is our major product that we see. Okay, so what happened here? So I look and see that my carbon that had 2 hydrogens, I do put a hydrogen on there, okay? But then this one, I would expect the iodine on it, and iodine's not there. It's actually right next door. What we see here is another hydrogen. Where did that come from? How'd that get there? Well, we'll get to that. The iodine that we thought should be here, like we have on this one, ends up all the way on this carbon here, the one next to it. We call this an allylic position because it's right next to a double bond. So it actually didn't add to the double bond, it added to an allylic position. How'd that happen? Why do we see that? Well, let's go through and figure out why this happens. Anytime we're trying to figure out why something happens in organic chemistry, we want to look at the mechanism. The mechanism always gives us a clue of how we're getting there, or it just outright tells us. But if we understand why things are happening in that step-by-step manner, we kind of run into it whether we realize it or not. So in this case, I've got my double bond, I've got my HI. We know the electron-rich double bond attacks the electron-poor hydrogen. It's electron-poor because iodine's taking its electrons. So double bond takes the hydrogen, and those electrons go to iodine. That's no different than what we saw before. So we get our carbocation, we would expect that. But we see that's not what our product ends up giving us is iodine attacking there. So what happens? Well, remember that we made this carbocation on this second carbon as opposed to the first one because a more substituted carbon, one that has more carbons attached to it, is more stable. So this is secondary. It's secondary because there's a carbon attached to one, attached to two carbons. If I look to the right, this one's attached to one carbon, so it's a primary. And that's why we didn't make the cation there. But if we look to the left, this carbon has 1, 2, 3 carbons attached to it. We know if we could make a cation out of that, tertiary 3 carbons is going to be more stable than secondary 2. So it finds a way to make it. How does it find a way to make it? It's the result of what we call a hydride shift. A hydride shift, a hydrogen and the 2 bonding electrons move over one position. We call it this because a hydride ion is a hydrogen with a lone pair. It's got a negative charge. And to get a carbon bonded to a hydrogen here, I need to bring 2 electrons with me. So what happens is this hydrogen with those 2 electrons skips over. It moves over one position. So that hydrogen and those 2 electrons hop over to the carbon to make that bond to that hydrogen there. But when that happens, this carbon, it loses electrons. It had 2, 4, 6, 8. 2 are gone. So now it just has 2, 4, 6. So that's a carbocation. If we look at that carbocation, so this one was secondary because it was attached to 2 carbons. This one is attached to 3. That makes that a tertiary carbocation. Tertiary carbocations are more stable than secondary. It's going to do what's easiest to do, and it's easier to make things that are more stable, things that are lower energy. Do we want to do things that are really high energy all the time, or do we just kind of want to slug around and do low energy stuff? Well, chemicals are the same way. They're going to do a lot of low energy things because it's easier to do it. So in this case, it could make something higher energy, or it could pass the hydrogen over and make something lower energy. If it's lower energy, it's more stable. It's more stable, it's probably more likely to form. So when that happens, and again, this right here, this is that hydride shift. The hydrogen shifted over one position. Once we've done that, our iodide now can attack the carbon. Iodide attacks the more substituted carbon, and it makes that major product. So that's how we get that product right there. We take the path with the easiest to form intermediate. We get it as a major product. So that's a hydride shift. The other thing we'll see is called a methylene shift. The methylene shift looks a lot like a hydride shift, but instead of hydrogen moving, it's going to be a methyl group. And I'm going to draw this using bond line formula just to make it a little bit cleaner. But it's the same thing that's happening. So this looks like the same compound we had, but whereas on this carbon we had a hydrogen and 2 methyls, this one has 3 methyl groups, so 1, 2, 3. What ends up forming as our product is this guy right here. what's happened is one of these methyl groups end up moving over to that position there, opening up this carbon for the chlorine. I'm going to draw the first part of this mechanism to show you how it's the same thing that we just saw. Double bond attacks a hydrogen. The chlorine pulls the electrons towards itself. Like we saw in the last one, hydrogen adds to the less substituted or more hydrogenated carbon. Carbon that's more substituted gets the cation. So once again, we make a secondary carbocation. If I look to the right, there's a primary carbon. That's not going to make a cation because it's not going to be stable. If I look to the left, there's 1, 2, 3, 4 carbons attached to it. That's actually called a quaternary carbon. We can't get a quaternary cation though because I've got 4 bonds to carbon. Carbon only makes 4 bonds, so I can't take one of those off to make a positive charge and still be quaternary. But if I could remove one of those methyl groups, that would give me a carbon with 1, 2, 3 carbons. That would be really substituted. We know it's going to be really stable. So what happens here again, this is called a methylene shift. One of these methyl groups and its bonding electrons slides over to the carbon. So we go from a secondary carbocation, and by moving that methyl group over, we got a carbon with 1, 2, 3 carbons, so it's tertiary. Both of these rearrangements made a cation that was more stable. The other one moved hydrogen because hydrogen's easier to move. And if I move hydrogens, I keep all those carbons to make it more substituted. In this case, I didn't move a hydrogen because there wasn't one. You can't do a hydride shift if there's no hydrogen to shift. So in this case, I can move one of these carbons, and that still gives me something more substituted than what I started with. Because there's what you got to keep in mind. I've got to have a gain somewhere. I got to make profit on this somehow. Profit in terms of energy. In this case, I'm secondary. Whatever I make has got to be more stable. If it's not more stable, it's not going to do it. Why do extra work if I don't have to? So secondary makes tertiary. That's more stable. It wants to do that. It's going to do that. So I get the methylene shift, and then I add my chlorine to the carbon. I get that guy right there. So that's rearrangements. I do my first step of my mechanism to get my first cation, and then I stop and look. Can I make something more stable off one of my neighbors? If I can make something else stable off one of my neighbors, I'm going to do a shift. Hopefully a hydride, or I'll move one of these methyl groups. But if there's not anything more stable next door, it's not going to do anything. It's going to stay where it's at. So that's rearrangements in addition systems. If you found this helpful, please hit the like and subscribe. This is Why Chemistry.